Hello, everyone. Thank you for joining us this evening. Tonight, we have a tech talk on design patterns by Ross Turker. Ross, whenever you're ready, take it away.
Thank you, Ari. First, I'd like to start by thanking Remake Labs for sponsoring this tech talk. My name is Ross, and tonight we'll be learning about software design patterns, specifically object-oriented design patterns. My goal with this talk is to help those less familiar with design patterns to understand them better. We'll go through each type. However, I've decided to focus more on some important concepts which can help you gain deeper insight into design patterns in general. We'll start by discussing what design patterns are. We'll then touch on why you should or should not use them. We'll get a conceptual lay of the land. Then we'll discuss the different types. Finally, we'll wrap it up with a few key takeaways. Design patterns are reusable solutions to common problems that occur in software design. Think about it this way. While an algorithm is like a step-by-step recipe for solving a problem, a design pattern is more like a blueprint, a higher-level concept of how classes and objects can work together to build a solution. An algorithm has a specific implementation, but a design pattern can be implemented in many different ways depending on the context. Design patterns are more common than you probably realize. Take the example of a simple for loop iterating over an array. The for loop looks for a certain type of method on the array object. Let's call it the iterator method. You can see the implementation in the class to the right. If the for loop finds this method, it invokes it. This method returns an iterator object, and you can see how that works in the class to the left. The iterator object holds a reference to the array and a next method, which the for loop calls until the iterator object indicates we have reached the end of the array. This is an example of the iterator pattern, which provides a way to access elements of a collection sequentially without exposing its underlying representation. This pattern uses the iterator method exposed by the array object. However, any object that exposes an iterator method could be iterated over. In this example, the for loop simply looks for that method and invokes it if it finds it. This method is part of the array object's interface. We'll come back to that shortly when we discuss important concepts. So why use design patterns? There are always trade-offs in software design, so let's touch on a few. Here's some of the benefits. Design patterns are reusable. They improve readability and maintainability. They allow you to create software that is both flexible and extensible, and they provide developers with a shared vocabulary. What are some of the drawbacks? Design patterns can introduce unnecessary complexity into your code. They can add performance overhead. Incorrect use of them can lead to inefficient or unmaintainable code, and there is a learning curve. Here are a few important concepts to keep in mind as we consider why we use design patterns and how they work. A function or method signature specifies its name, parameters, and return value. The set of all method signatures defined on an object is called its interface. In essence, an object's interface exposes all the ways in which other objects can interact with it. Any request that matches a signature in the object's interface may be sent to the object. Interfaces are fundamental to object-oriented systems. Objects are known through their interfaces, but an object's interface says nothing about its underlying implementation. Method A on one object can have the same signature as method B on another, but their underlying implementations can be completely different. Why does this matter? Different objects can support identical requests based on their interface, but they may have different ways of processing these requests. Requests are sent to their receiving objects at runtime, at which point the request becomes associated with the receiving object. This is called dynamic binding. That is, the association happens at runtime dynamically. What this means is that the operations that act on the incoming requests are not chosen until runtime. This also means you can substitute objects with identical interfaces at runtime. The ability to substitute objects with identical interfaces is known as polymorphism, which is another key concept in object-oriented design. This means you consider the object's interfaces when deciding how objects interact. This lets you decouple objects from each other and have their relationships to each other vary at runtime. I know that was a lot, and I only go so deep into this because you will often see this pattern amongst the more common design patterns. Classes will inherit interfaces from other classes, or objects will be defined with similar interfaces to other objects, and then connected in certain ways to extend their functionality. This allows for a lot of flexibility and reuse in how the system is created or maintained. These two types of reusing functionality are called class inheritance and object composition. We could go much deeper into this, but for now, I just want you to remember these concepts and think about how much flexibility it can afford you when you start to think and build in terms of interfaces. If one object can make a request to another object with a certain method signature, that receiving object can be substituted at runtime as long as the substituted object has a method with the same signature that can handle the request. It's a very powerful concept. There are three main types of design patterns: creational, structural, and behavioral. Creational patterns provide various object creation mechanisms. Structural design patterns explain how to assemble objects and classes into larger structures. And behavioral design patterns describe ways of communicating between objects or classes. All of these patterns share the goals of providing flexibility, efficiency, and code reuse. There are two subtypes of each pattern, and I've broken out each subtype in the following slides. You have class design patterns and object design patterns. Class design patterns deal with relationships between classes and their subclasses. These patterns use inheritance to create fixed compile-time relationships between classes. Once defined, they cannot be changed at runtime. On the other hand, object design patterns deal with object interactions and compositions. They focus on how objects interact and how they can be composed to form more complex structures. These patterns use composition rather than inheritance, allowing for relationships between objects which can change at runtime. So let's dive into a few quick examples. Here's a simple implementation of the factory method pattern. This creational pattern provides an interface for creating objects, but allows subclasses to alter the type of objects that will be created. I've highlighted some key things to focus on. Remember how we discussed interfaces and method signatures? Notice how the orange methods all have the same signature as do the green ones. A factory method is called factory method in each case. It takes no parameters and returns a product. The operation method is called operation in each case. It also takes no parameters, and it returns a string. In this example, the base creator class, this one right here, at the top left, defines an interface with the factory method on it. However, the actual implementation of that method is left to its subclasses, namely concrete creator 1 and 2. Each of them overrides the base class's factory method with its own implementation. The concrete creators in this case return an object, the product. You can see the two product classes at the bottom. If you've never seen this type of design before, it can be confusing. However, a few things to note. You can see the client code on the top right, which uses a creator object. It doesn't know much about the creator class other than its sum operation method, which you can see in red. This allows for flexibility. The client code is expecting a creator, which means that any subclass of creator is fair game. Since all subclasses inherit the sum operation method, you can pass any concrete creator into the client code and it will work. I've included a familiar use case in React. Both snippets do the same thing, here and here. But the main takeaway is that React exposes the simple interface we can use to create any type of React element we want just by changing the arguments we pass. In this example, you can see another familiar use case, this time using an adapter. The adapter pattern allows objects with incompatible interfaces to collaborate by making one interface conform to another. In this case, Express is expecting the cookies from the incoming requests to be on Express's request object's cookies property. Right there. While the incoming request is sent over as JSON, the cookie parser acts as a go-between. It grabs the cookies from the JSON object and puts them where Express is expecting them to be. In this example, Node's event emitter class implements the observer pattern. The event emitter allows multiple listeners to subscribe to specific events. When an event is emitted, all registered listeners are notified and execute their callback functions. An example there. This pattern is essential for building event-driven systems where changes in one part of the system need to be propagated to other parts efficiently. I'd like to leave you with a few final thoughts. With practice, you'll learn to spot common design problems and have an arsenal of reliable solutions at your fingertips. As you become more familiar with common patterns, it will change the way you think about software. Where you once created a solution from scratch, you will now have a library of heuristics to lean on, so you can build upon the experiences you've had and solutions from the past. Remember, there's always trade-offs when it comes to design decisions. Sometimes implementing a design pattern will have more benefits than drawbacks, but then there's other times where all you need is a simple function. Here are my works cited and my contact info. Feel free to reach out anytime. And I'd like to once again thank Remake Labs for sponsoring this talk. Thank you all for joining me and have a great night.
Thank you, Ross, for such an insightful talk on design patterns. And thank you all so much for coming. Have a great night.